This video is the second video on the distribution of chemicals. Here in this video, you will be using engineering heuristics to help you build a process flow diagram. We know that we're chemical engineers, right? In chemistry, we have a regular chemical reaction, but in chemical engineering, we need to deal with it and we need to make that chemical reaction happen. And our goal as chemical engineers is using the chemical engineering fundamentals to be able to build something like this, right? Life is tough and we need a way to start. So how to decide? In process synthesis, what we do is that we use heuristics to rely on intuition and experience while building the base case flow sheet. And then what you do is based on the different constraints of your scope of work or project statement, you optimize this base case to generate the most promising process flow diagram. The first heuristic that we're gonna deal right is basically use an excess of one chemical reactant in a reaction operation to completely consume a second valuable toxic or hazardous chemical reactant. We did this preliminarily during our concept selection process, right? We considered safety. We basically evaluated multiple reaction pathway using preliminary data table to make this decision. So we were thinking about this heuristic since the beginning. However, at the end, we will get back to it to make sure that we are meeting, right, this heuristic as much as we can. Then the second heuristics involve excess reactants. Use an excess of one chemical reactant in a reaction operation to consume completely a valuable toxic or hazardous chemical reactant. The material safety data sheet will indicate which chemicals are toxic and hazardous. And this is why we build a preliminary data table. We need to take this into consideration across the different stages in our process development. For example, in our vinyl chloride, what we can do is compare chlorine and ethylene, and basically we try to consume completely the hazardous and toxic chlorine, but the recovery of unreacted ethylene from the dichloroethane product is required. And this is where the optimization part comes. We know that we need to recover, right, that ethylene to send that back in the first reactor in this example. And many of the things that we do is to optimize that ratio, right, of recycle back in the process. Heuristic 3 involve when nearly pure products are required, eliminate inert species before the reaction operation when the separations are easily accomplished and when the catalyst is adversely affected by the inert. Examples are when you have, for example, syngas, natural gas, air. You may have some components there that may be poisonous, right, for the catalyst, or may be affecting the separations later. Do not do this when a large exothermic heat of reaction must be removed, because inerts actually help us to absorb some of the energy from an exothermic reactor, helping us to control the temperature inside the reactor. So, right, there are different ways that you can do this. You have reactant A, B entering into the system with impure feed C and D. What we can do is decide in what stage we want the inert to be removed from the process to be able to produce pure E and F, which are the products of the main reaction. Something that we forget is that even that in the simulation we add the pure ethylene, for example, we may need to check our sellers because ethylene may not come pure, right? It may come with a percentage of another contaminant because the purity of the ethylene or the raw material affects directly the price, right, of purchasing of that particular chemical. So sometimes we sacrifice low purity and then remove that before sending it into the reactor if needed. When we handle inerts, right, we need to decide whether to remove inerts before the reaction or after. Okay, we can do it in different stages, right? We can do it before it's sent to the reactor number 2 or after it passes through reactor number 2. And the amount of inerts not only affect the heat of reaction, the absorption of that heat of reaction if it's an exothermic reaction, but also affects the sizing of the reactor. Now you have to process a lot of material if the amount of the inert is a lot. So it's a big decision to make and something that you need to consider when you're building handling that distribution of chemicals, especially in the early stages. Clearly, the ease and cost of separations must be assessed. This can be accomplished by examining the physical properties upon which the separations are based and implies the use of simulation. Heuristic 4 introduce purge streams to provide exit for species that enter the process as impurities in the feed if you don't remove them, are formed in irreversible side reactions when these species are in trace quantities, are difficult to separate from the other chemicals. Remember, lighter species live in the vapor purge stream and heavier species exist in the liquid purge stream. One of my advice at the beginning is everything that is coming in the exit of that reactor or reactors, you should arrange that initially in order of volatility, because that will give you an idea of the order, right, of the chemical, right, and how it's going to leave the separation, if it's going to be in the vapor or in the bottom. So this is the example with the ammonia synthesis loop. You may need to have a purge where you recycle back some of the hydrogen and maybe the argon and the methane. And we do this because the separation of argon, methane, nitrogen, and hydrogen, it is really hard to accomplish. You probably need cryogenic separation, and this could tend to be very expensive, especially also if you have volatility that are close together. This may be a challenge. So sometimes what you do is you decide to add a purge to make sure that the trace chemicals, they are removed from the system and you have an operation that is under steady state. The purge flow rate selection depends on economics. So this is, again, as a recycle, something that you need to consider in your optimization. In Heuristic 5, do not purge valuable species or species that are toxic and hazardous, even in small concentrations. Always remember to check back to the MSDS. Add separators to recover valuable species. Add reactors to eliminate, if possible, toxic and hazardous chemicals. And I think one of the most common processes like that is actually the combustor in your car, right? You have a catalytic converter that is put after the reactor just to mitigate the NOx and the carbon monoxide. It's not that the carbon dioxide and the nitrogen and the oxygen and the water and all of that mixture is actually beneficial. Is that it's less, for example, the CO2 and the nitrogen particularly, you're having now a component that is safer than the inlet of the catalytic converter. So basically you're mitigating this. Also think about that if you have something in the waste. First, before you call it a waste, you need to design something to mitigate those chemicals. Things like carbon dioxide, for example, in companies that are energy-based companies that produce energy, they have carbon dioxide in what is called the flue gas. And what they do is that they do absorption methods using amines to remove and mitigate the CO2. Heuristic 6 tell us that byproducts that are produced in small quantities in reversible reactions are usually not recovered in separators or purged. Instead, they are usually recycled to extinction. Remember that if you have a reversible reaction and then you have a byproduct there, when you send that back now to the reactant side, right, recycle it back, then you're consuming that in the chemical reaction because it's in equilibrium. So now with the side reactions, I have told you that side reactions are important to be added to the reactor. For competing series or parallel reactions, adjust the temperature, pressure, and catalyst to obtain high yields of desired products. In the initial distribution of chemicals, assume that these conditions can be satisfied, obtain kinetic data, and check this assumption before developing a base case design. So this is the stage that we are right now, right? We are trying to gather that information, and then once the base case is close to final, right, then we're going to corroborate those assumptions in the process. So things like conversion, selectivity, the actual reaction in those side reactions are important to have them. Also the temperature and pressure conditions that they operate, right, and have them ready for use in our reactors. So this is just a summary of the multiple reactions and selectivity. You saw this in your kinetic course. This will be important when you add the reactions into the reactor. You need to indicate the ranking. And that ranking is based, of course, on the meaning of the different type of chemical multiple reactions and selectivity. So here you have the parallel competing reactions. You also have the series reactions in series, reactions that are both in series and parallel, and you may have other complex reaction happening in the reactor. So it's important that you know the order, that you know which reaction happened first and which one is second. So you're able to add that into the simulation. Here, the desired product is marked by the red box. This is an example on how important the kinetic information is. So this is the manufacture of allyl chloride, and here on the right side you have the heat of reactions and kinetic constants for the allyl chloride process. You have the 3 different reactions, right? You have reaction 1, which is the one that produced the allyl chloride. Reaction 2 produced the dichloropropane, and then the reaction 3 reacts with more of the chlorine, right? That is part of the reactants in reaction 1 to produce the dichloropropane. Notice that this involves 3 competing second order exothermic reactions. You know that the reaction is second order just because of the units of the rate constant. If you look at the table, right, we notice that the rate constant for reaction 1 is in between, right, the rate constant of reaction 3 and 2. So when we are looking here at this type of reactions, when selectivity is the key to the success of a process design, it is not uncommon to carry out an extensive analysis of the reactor alone before distributing the chemicals and proceeding with the synthesis of the flow sheet. In our case, we don't have the luxury to have a research and development department that they can do more experiments and give us this information. If you work in the industry, this is where you take advantage of your resources. But in our case, we need to find the correct literature. We need to really find literature that help us to understand as much as we can the kinetics in the reactor. In other cases, right, using simulation models, the distribution of chemical is carried out as the process is optimized to achieve an economic objectives. Sometimes in the process simulator, you can assume some things if you're missing information, so you have to be very careful at what things you add into the simulator. So the question is, with all of this kinetic data, what temperature conditions reaction 1 is favored, right? So here what we do is what we collect kinetic data, right? We have some points here, and we can actually linearize the Arrhenius equation and basically have a relationship between the rate constant, the activation energy, the different temperatures, and the natural log of A, which is the pre-exponential factor. So with that, what we can do is create a graph, right? Varying the different temperatures. This equation, the slope and the intercept of this equation can be obtained with the reactions that you have here. Use that data to actually create a linear equation for this graph. The linear equation that describe the behavior of this reaction. Anyway, so what you end up having, right, is graphs like this, where you can compare the different rate constants, the natural log of the rate constant. And what we are looking at, right, is at what range of operating temperatures favors production of the allyl chloride, which is reaction number 1. So we can see, right, that region B, particularly, the rate constant of the desired reaction 1 is the largest relative to the rate constant of the other 2 reactions at the intermediate temperatures. So here, if we control the temperature, we're able to favor one reaction over the other, right? How selective it is at this condition becomes also important, right? We are increasing the selectivity by increasing the speed of the reaction at those particular conditions. So when you're dealing with multiple reactions and selectivity, you have to make some calculations and assumptions. So this is just a summary of the different meanings, right, of conversion, selectivity, and yield. Using this, if you have the selectivity and the conversion, you can actually get the conversion of the side reaction if you don't have it, but if you have the selectivity, it helps. So you can go back and forth between these calculations to kind of collect all the information that you need to add into your reactor. Heuristic 8 still works with side reactions. Here, for reversible reactions especially, consider conducting them in separation devices capable of removing the products and hence driving the reaction to the right. So it's like it's something that as it reacts, it extracts at the same time. Such reaction separation operations lead to very different distribution of chemicals. An example, right, is the reactive distillation. Here on the right, you have an example with the methyl acetate production. Reactive distillation is used when there is a significant difference in the relative volatility of the chemicals at the conditions of temperature and pressure suitable for the reaction. If this difference doesn't exist, therefore, in one single column, you're not gonna be able to have the temperature distribution to extract while you're reacting. In a conventional processing, when a reversible reaction operation is followed by a distillation column, it is common to use an excess of a feed to drive the chemical reaction forward, right? To move that equilibrium reaction from products to reactants and favor that conversion forward. Alternatively, when the reaction takes place in the gas phase, the pressure is raised or lowered depending on whether the summation of the stoichiometric coefficients is negative or positive. And this is important, right? This is basically what we're using is the Le Chatelier principle, right? We're working with the total number of moles in the reactants and the products, and you're changing the pressure, right, to favor the products in this case, right, when you have a reversible reaction. So far, all of this heuristic help us to build the reactors. You may have one or two reactors, like here in the vinyl chloride example, I have two reactors. You can use adjust to calculate the feed composition based on the specifications on the product. You can also use sets, and the set basically allows you to calculate the amount of reactant compared to the limiting reactant, and this allows us to specify if the stoichiometry is 1:1, if you have something in excess. Typically, you start with 1:1, right? Or the stoichiometric, depending on the stoichiometric amounts in the chemical reaction. And then after you do that and you add a recycle, probably that it will be kind of in excess if you don't allow the fresh feed of the reactants to be adjusted or modified as you add the recycle. Talking about recycles here, right? You need to start planning those recycles. So at this stage, I just recommend you to start thinking about the different molar flows, right, of the different chemicals. Think about the volatility. So I will probably arrange my components in HYSYS, right, or in my simulator in the order of expected volatility. Notice that the order of expected volatility helps you to define a separation sequence if you don't have an azeotrope, right? When you have an azeotrope, like working with alcohols, there's differences there, right? But at least it's a good starting point just to know where are they located in relative to each other. You know, once you have the reactors, it is good that you start thinking of potential separation units. Remember that at this stage, because we're distributing the chemicals, we're not adding any heat exchangers, we're not adding anything, right, that relates to the heat transfer. We're not adding the actual separations. We don't know at this stage if we need a flash tank, we don't know if we need a distillation column, we don't know if we need liquid extraction. So basically at this stage, what you need to do is you create your block flow diagram, kind of having a vision of what you should be having in a couple of weeks from now, right? When you start gathering the necessary information of the exit of your reactor, basically. So with this, we conclude the distribution of chemicals. Make sure that you watch the videos online involving the simulation training to complement this lecture.